on the left one. Close. Celui-là, non?
Ouais. Ouais, just click.
Okay. Bon. Et là, il peut dehors, il peut dedans. So, logiquement, je devrais commencer par ça. Non, c'est pas vrai. On peut commencer par celui-là. And still wait a little bit. Okay, so I can put this one here. Remember which point we went last time? Control semantics. Ah, à peu près ici, je pense. Ok, ici la composition. So maybe you can.
Yeah.
Okay, so welcome to this 7th lecture. So last time we showed we have seen how to define the semantics of the while programming language using an inductive definition. Maybe I should go back to the definition to have this in mind. So basically we have the language here, just a short reminder. So with the skip assignment sequence if and while construct, And in order to define its semantics, so we have the semantics of expressions as usual using get and update functions. Get, sorry, just for evaluation. And update is needed when we try to define semantics. So remember that it's impossible to define the semantics using a total function, which is called here eval w, because here we have a recursive call, which is not structurally smaller than the original argument. So we have to go to another technique, so which consists in translating a function, here a function with an input in winst and another input in state and an output in state. So you just take exactly the same thing here, an input, another input, and an output, and you return a proposition saying that, okay, these three things are related according to the relation you want to define. And this definition is written exactly using the same formulas. Okay, for instance, for the assignment, which uses the update function on the state. Okay, you will find. Okay, well, we'll find it. Sorry. So this one, okay, goes exactly to this place. This is the output of the relation in the case where we have an NS-assigned constructor for the relation. Okay, so the name of the relation, first input, assignment, the case you have here when you use pattern matching on a function. The state S is the same as here. This is state S, which is the input, and the output is exactly the output you want to return in this case, and so on. Okay, and here you don't have a problem at this place because you don't claim here that you can compute it. You just claim that if you are able to make a proof tree, its conclusion will state that you have the expected relation. For instance, for the while true here, the last one which could not be expressed before, you say that in the case where the Boolean expression evaluates to true, and if you have, if you are able to go from S to S1 using instruction I, and again from S1 to S2 using the whole loop, okay, so body and, okay, so then you are able to go from S to S2, okay, using this, okay. So you just state what is the expected input-output relation, and that's all. And then what you have to do is, for instance, to check that you are able to make a corresponding proof. For example, for specific cases, so we considered a program P1, okay, which corresponds to some program. This one in textual form. And then you can prove that with this program P1, you can go from some state called S1 defined before to some state called S2. And basically, you only have to, you can compute from time to time to see, for instance, the expression here, what is its value in this state, okay? And then basically, you just apply the rules such as NS while true that we have seen just before, and so on. You can use NSSEC, NSAssign, and so on. Okay, so you make a proof tree, just a big proof tree that you can draw by yourself. So this is the bottom of the tree here. Okay, so you have the conclusion, and on top of this rule, on top of this bar here, which has the name NSY true. Okay, you have 3 conclusions which themselves have to be proved by their own proof tree. Okay, so you have to keep in mind that this is the kind of object that you deal with, that just trees, like as usual, just trees, with a somewhat complicated shape, because you have rules, name, and okay, here it's a little bit short because actually NSY true has other arguments, but they are just replaced by the name of the program, the name of the state, etc. But basically, you recognize what you want. Okay, and when as soon as you understand that you play with trees as usual, you can also make proofs on these trees as well. You can make proofs on proofs. Okay, so this is what we have. This is the exercise we have done last week, for instance, with even. Remember, so here the proof tree was a very simple branch, only a stack of even justified by the previous evens and so on. And okay, we were, for instance, able to prove that from the proof of even of n, okay, and another proof tree of even of m, you are able to construct a proof tree of even of n plus m. And that's the same, so we can do very simple exercise, very specific, constructing a proof tree, and then we can do so the next exercise I proposed to you was, okay, so this one, okay, so it is exactly the same. Here we have a more complicated program with more complicated states, but basically it's the same, making a proof tree for specific values. And then we could do something a little bit more interesting here. So I don't know if you tried. You can prove, here you reason not on one program, but on a family of programs. So a family of programs, which is called P square, and here you have a parameter n, which is the constant value that you want to reach. You want to compute the square of n, actually. Okay, so, and in the same way that P square 2 computes here the square of 2. So at the end you have 2 here and 4 here and 5, which is okay, some other memory cell. So actually P square n is exactly P square of 2 is exactly P square 2 in one word. Okay, so we just add a parameter. By the way, you can see this here. P square 2 is this program, this AST, with a 2 here. Okay, and in the case of n, you have only n here. So you see it is exactly the same program with the n fixed in advance, but an unknown n. So you have a family of programs, and then you can prove something that you have to guess, actually. So the thing to guess is the following. Okay, so maybe I will state the theorem to be proved. In that case, it is something like P square. Okay, let's call it P square n. Okay, so it would be something like, for all n, P square of n, starting from the same initial state, will end with n here, an n times n here, and don't know if you guess the value it should be here. So it's something like 1 plus 2 times, and you can write it in different ways. Okay, so actually you can see this formula, this sequence of formula here, as a kind of invariant, which is satisfied by the loop. Okay. So okay, but the point here, okay, so okay, here you have to think a little bit how the program works, but this is as business as usual, I would say. Think a bit what you are doing and find. In order to prove this, basically you don't need especially new techniques. It's just a proof by induction on N. And it will work. Why? Because after, okay, you have two cases. The idea is that you have two cases. Either N is 0. In that case, okay, so you just exit the loop from the very beginning, and you see that you start from 0, 0, which is the square of 0, and 1, which is 1 plus 2 times 0. So you see easily that at the beginning, you have your invariant. And next, in the induction step, say that if you have this formula for N, then you will have the same formula for S of N. And this is because if you have S of N, you see that in that case, the loop of the body has to be, sorry, the Boolean expression at the very beginning here, okay, I is not equal to to N actually, and so this value is not equal to N. So you have to perform the body of the loop once, and after performing the body of the loop once, oh no, it's not okay. Sorry. Okay, you have to think a little bit more. Yes, because actually, okay, after one turn, actually, you get one and 3, and then okay, so you see that here you see that the how to say the formula is not powerful enough, so you have to remember something which is close to what we have seen for proving things on programs with accumulators. Actually, so you have to prove a more general statement here. So you have to find it. This is actually what I said that you okay you need okay fine you need to think a little bit more. The point actually you can see that because this formula here is like basically it's a little bit like this program here. I mean, okay, this inductive definition of a relation mimics this function, and you can see that this function use the state S here as an accumulator. At each recursive call, the state is changed. Okay, so you have to reason on. You have to say something such as for all S such that blah blah blah. Okay. Okay, so okay, I have a solution. I have a solution, of course. I would not raise an exercise which has no solution, but okay, it's feasible, and okay, basically, my students in France, many of them are able to find the solution. So you should be able to do that as well. Okay, so the main point is that. You can do proofs for this kind of statements. So using techniques we have seen before. And now I would like to show that we can do much more. We can prove things. Oh yes, so by the way, in the course of the proof, you need to use very basic lemmas of arithmetics, and I think that only these ones are useful. Commutativity of addition and associativity of addition, this kind of thing. Okay, yes, because maybe okay, maybe it would be a good idea to an alternative that you can consider is to write this like this: n plus n. So you avoid multiplication. But anyway, you need n times n here. So probably you need something on multiplication as well. Okay. Okay, so now what you another thing you can consider is something which is related to compilation, kind of optimization of the source code. So you want to remove useless tests. So the useless tests considered here are when you have an if statement with an expression which is just be true itself. So it's rather stupid to write this, but okay, it's allowed. Why not? Then you just say, okay, in that case, I just remove the test, the runtime test. I directly say that I replace the program by the else, by the then branch. And similarly, if you have a default, you replace the statement by the else branch. And here, okay, so the here basically is completely obvious. You have to put I2 here. Okay, in the other cases, it's wrong. It is not I. It is if you have okay, like sequences. Okay, you actually what remains is a while loop. Okay, so in the case of a while loop, you also want you have to make a recursive call as well. Okay, well, we can leave it for short if needed, but because actually there is nothing. Okay, so the interesting part is not there, so we can keep it here. Okay, so what is interesting now is that okay, is that we can write this statement. So if the original program here returns S prime from S, then the simplified program okay, relates S and S prime, the same S and S prime, okay? So the transformation is correct. So nothing surprising. So let us try to this. So okay, something was left before. Okay, because I forgot to. Okay. Okay. So here our statement. Okay, so nothing new. So as usual, we introduce the instruction I. And okay, here you are careful because SIS could move. So I keep them in the statement to be proved. Okay, so you remember the induction on quantified formulas. So let us try to make the proof on I. Okay, so okay, so we get all the cases, possible cases for I. Okay. And then, okay, let us see the first goal. We can, okay, maybe we should do that to see it better. Okay, just to remove the other goals. And you see here that something is not very good because we have this statement here, which intuitively should enforce S prime to be equal to S by the very definition of NSKip. Remember that NSKip is satisfied only when these two states are the same. Okay, so I expect to have S and S here as well, and because otherwise I cannot just okay. Let us CBN to see what happens. Oh, actually I can. Actually I can by chance. Okay. But for the other goals, it will be more complicated. It will not work as simply. Okay. Yes. For this one is too simple. It still works. Okay. Let us okay. Let's try. Let's just check. So we say exact ns, for instance. So for the next one, okay. So it still works. Yes, because okay, that's the same. Okay. So here we have a situation where actually the hypothesis happens to be exactly the goal. So we don't need to, actually, we should have more information. That is, for instance, S prime is obtained by updating of blah, blah, blah. But actually, we are somewhat too lucky here, and we can just reuse this hypothesis for free without, okay. So let us. So this time, I think things will be more complicated. Yes. What should happen? Sequence E1. Ah, maybe it's possible. Maybe it's possible. Okay, but anyway, as I said to you, we even if it works, we are very lucky. Okay, basically, when you okay, so I go back to what we could see here. So once again, what I would prefer to see here S and S, because this is really the full information I should be able to get. Okay, so let us forget about this this fortunate tries, which maybe I'm quite sure that if you go later, you will it will not work. Okay, so the observation is that okay. See what is written here. Okay, we should get S is equal to S. We should get the same S and S prime, and that's not the case. Okay, so so how to get this? So this is here where where we can do better than an induction on I. We can do an induction on this. Okay, so remember that this one. So let us introduce all of them. So what you have in your pocket is I, S, S prime, and the fact that I, S, and S prime are related with the NS relation. What does it mean? It means that you have in your pocket a proof tree of this for this formula. Okay, so you have a tree, and as any tree, you can reason by induction on it. Okay, that's the very point of the of reasoning by induction on inductive relations, not on inductive types, but on inductive relations. So in this case, the nice thing to do is to say, okay, actually, I will reason by, on all these possible trees, and as I reason on these trees, their conclusions will be enforced by the specific constructors that you have. For instance, okay, once again, it's better to have the constructors on your eyes here. Okay, so okay, so you will reason on the possible ways of making a proof tree using these constructors here. Okay, and for instance, you see that for the first one, just take the first one, but for the other, it's the same. For the first one, you say not only that, okay, you have this proof tree, but having this proof tree enforce these two S and S prime to be actually S and S, S and S, okay? So let us perform the induction NS. So here I am very accurate. Usually what you do is just to say induction NS, you see what happens, and then okay, it's better to have your own names here. Otherwise, your script will depend on names produced by Coq, which is not very robust. Basically, when you program, you like to have the control of the names that you use. You don't want the compiler to say, okay, please take this name. Okay, so for instance, for NS, I have one argument, which is S. For assignment, we have three names. The name of the variable, I call it X here. The name of a state, I guess, and here, okay, we will see. Yes, okay, we will see what it is anyway. We could look at the source code and to see that. So I do two things at the same time. First thing, induction, and then as the instruction will be a little bit specified on each one, we see what is at the root of the AST. So it's an opportunity to what is returned by this function in order to have simpler goals. Okay. Otherwise, if you don't do that, okay, you can do this CBN on each separate case. Okay, and then you get goals which are much more convenient. Okay, so okay, so let us complete here, for instance. So first goal. So here, okay, you see that I just have to prove that I can go from S to S using skip. Okay, so actually this skip is obtained by computing simple test, blah, 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 on skip. Okay, this is this one. And the S comes from the fact that you were considering the NS skip of the source code. Okay. So okay, what you see here is exactly what you expect. Okay, so you will just say apply, for instance, or NSKip, or exact NSKip apply to S, if you prefer. Next one. So this is for the update. So here, once again, it is exactly, so actually the transformation did not change anything, so you will just say that this one is obtained by the NS assign constructor. Okay. So the proof is much more natural than before. Before we could do it by chance somewhat, but this time it's okay. So sequence, you get this, and here, okay. By the way, you have no complicated statement on with for all. So here again, you will just use the induction hypothesis. So you should probably say something like apply NSSEC with okay. If you just say that Coq will complain that you need to say what is S1, but S1 is just this S1, which is obtained here. Okay, so the original one. So say with S1, or you can use refine with more the number of wildcards. Okay, and then you see that you exactly have your induction hypothesis. Okay. So you could say for the first one, exact this one. And for the second, the same. The 2. So I think this should work if I am not wrong. Yes. So here, by the way, I show you another possibility you have with the tactic language, which is the following one. Here, if I put a dot, you get 2 sub-goals. And if you know how to start to here, I even know the full proof. But what I say is that on the first sub-goal, so I open two brackets. I open a bracket here, which is closed here, with 1 bar here for saying that here I am expecting 2 goals, 2 sub-goals, and for the first sub-goal, I will perform this tactic, and for the second one, I will perform this tactic. Okay, so it will finish or not, I don't know. Actually, it will finish in that case. So okay, it allows us to handle two sub-goals at the same time. Okay. Okay, here we come to the interesting case, because until now, actually, the simplification function, this one, did not perform anything interesting, except maybe here where it is recursively called. So we just use the induction hypothesis for the 2. But here we are in the interesting case where, so there is something to do here. And okay, so here, yes, so something will be a little bit tedious here. Okay, so what you can see, so you have to be careful here. Here you have a Boolean expression. This Boolean expression could have this shape, or any other shape. Okay. And here, we don't say, for instance, that cond is be true. Be careful. It just says that whatever the contents here, so which would be this case, or whatever other case, the evaluation using this function will return the Boolean value true. Okay, so you cannot, for instance, rewrite this e. It does not make sense. You don't have this expression here. You just have cont. And so basically, at the moment, you are still not able to use this equality. So the only thing we can do in this situation is to actually follow the program. So we see that we should perform a case analysis on cond. So we have as many cases as explained or expressed in the bexp ist. Okay, so all these cases here. So the basic thing to do, actually, when I see that, I would like to write a refine. But anyway, it makes sense only if I am able to answer very quickly on this. So at the moment, I will be careful. Okay, so I will just proceed by a destruct on cond. So this goal will be And I don't want to make an induction on count at this point. I don't think it's a good idea because, okay, we will see, but intuitively, I think that we have enough information here. So I try with a simplest possible tactic. So it is just destruct. So I should write, if I am correct, with a number of cases, but I don't remember how many cases I have. But Coq will tell me. 7. Oh, okay. I said that it is tedious. But okay. 1, 2, 3. How many? Something like this. So, okay, maybe one is lacking. I don't know. Yes. Okay. And if you are still more, okay, I should add my own names, but okay, I am a little bit lazy right now. Okay. So sub-bullet. So the first case corresponds to the case I had true. Yes, for this one, we can see that we can just use the induction hypothesis. Yes, the reason is exactly the one you should have in mind, because you know that we are just considering the be true case. So in the case of B2, we replace the full instruction by I1, so I get exactly this one. So it's normal. It's okay. It is reasonable to use this one. So you can just see what you have, okay, and go on and move on. But you can also think a little bit. It's not a bad idea to think a little bit. Yes. So next one. So the point is that in that case, we have this condition here, which is interesting. Means CBN in E, so you can compute in a hypothesis. Okay, so false is equal to true. Okay, so here we recognize an interesting situation, what we call usually an absurd hypothesis. Okay, so the standard way, when you know what you do, is to just to say, okay, here I have an equality between two constructors which are different, not the same constructor. So you can okay. So okay. So either you know the Coq tactic for that, or you remember how it is justified. So last week I told you that there is a technique, a funny technique called contagious equalities. Okay, which allows you to replace anything by anything else as soon as you have a stupid equality like this. Okay, so here the game would be for instance, you could conclude that, for instance, I2 is equal to this one. One way to use what you have without cheating with discriminate. Okay, you could say, okay, from this force is equal to true, I can so I introduce a function which okay, so something like this. Okay, so suppose okay, let us call it F. I think I need a parenthesis. Let us suppose F of B, which is a Boolean. Okay. Bool, think. So if B, so So when it is true, say it is I2, for instance. Else, okay, just copy paste this one. Okay. Yes. So I can say that this one is actually change E2 with f of what? F of what did I say? True. Okay. Or I could do the, okay. Anyway, it's F2 parentheses. Okay. Now I will use my equality. So in the opposite direction in that case, so I could do rewrite. So in this arrow, to say I use the equality from left, from right to left. Okay, E. Okay. Well, no, I can just say it is just AHNS. Or let us CBN to see that. Okay, exact. So you see, oh, takes a little bit of time, but not much. And IHNS. Okay, so one way to finish it. So otherwise, okay, so once again, the standard way to do that is the following. So I should undo how many times? So maybe I will. So I have one pause and then let me see. One thing, one pause, one change. So I think that undo two should be okay. Okay. So okay. So the usual way would be to say discriminate, which is shorter to write. E. Okay. And then we have many goals. Let me see. So, so you know this. So actually, c'est quoi le truc? You know that it is true. So basically, we should go. Oh yes, yes. So we just apply because we okay. We know that we have this condition. Okay. So I think we can apply the. Don't remember. Yes, this one. Okay, and we have this condition, so it is satisfied. Okay, maybe NF is true. Okay, exact E. Sorry. So for the I will just remove the first one like this. So I say that the first goal is cancelled immediately, and then I have to prove this. Yes, by NS. By NS, actually. I don't need the induction hypothesis. And all of the cases are dealt with in the, I mean, all the cases for the Boolean expression will be dealt with in the using exactly the same, using exactly the same way. Let us try. Okay, I think, okay, I will try just a copy paste. Yes, so you see it works. Okay, so maybe it's better to write this way. Okay, so now I will just copy paste this one. And okay, so and I do it many times. So it is not very, it's a little bit of ugly, okay, but I think it works. How many times? Okay, I have finished all my stupid goals. So it's a little bit boring to write. Still, I was somewhat clever hit by using the semicolon and this one. But I would like to what I would like to say at this point is that for many cases, all the last one, I would like to perform this tactic, this set of tactics, for this sequence of tactics. So in order to use this sequence of tactics in these cases, but not all, because it will not work in the two first cases, which are the interesting cases actually. So what I can do is to say something a little bit weaker. I say try this sequence, and it works. Let me see. Yes, it works, etc. So, and even this one, I could try it at the very beginning. It will not work, okay, actually, but let us say, for instance, for this one. Sorry. I will put it here. Okay, so I have this goal. I try. Expected failure anchor expected one. Why does it not? Okay, because what I would like to do is to have this. Maybe this like this. Maybe. Yes. Okay. So this is so you see, I am experimenting the right thing which can be applied in all cases. Okay. So see, I was somewhat lucky here, but okay, I can make check that it will work as well. So of course, this one is not interesting here. It just does nothing, and then I go on. Okay. So now I try this one. It works. Okay. So what I am saying is that now I have a good sequence of tactics which can be used in all cases. So what I'm doing is to put it here. Oops, sorry. Just copy paste like this. Okay. So remember, so I have the sequence. I am able to do it. Now I have the interesting case of if statement with a count. I need to reason by cases on the possible forms of a condition of a Boolean expression. And I say that, okay, I will consider all the different cases. So there are 7, but actually I could, okay, in that case, maybe it's not very interesting to put this. I think it's more relevant to just say, I just consider different cases, and in all cases, I try this. And I have now only 2 cases to which are left, the 2 interesting ones. So I was able to remove the stupid ones. So, okay. And then we can play with contagious equalities or discrimination. And okay, so now the script is looks better. Okay. Okay, and okay, so now we have the converse case, which is which can be dealt with in a similar way. Okay, so this is now the case where okay, I was in okay, now I have the converse case where cond is evaluated to false, it will be, it will be dealt with in the same way. And the NS, and for the and for the what, the NS wild case, actually I will have nothing to do because I was lazy. I cheated a little bit here. Yes, I removed the. I just said that I just made I copied them. I should actually make a recursive call. Okay, but no, you can finish by yourself. There is nothing new here. So what you have to remember is when you have a sequence of boring cases like this, what you can try to do is to find the right sequence of tactics which will which can handle all the simple cases in some sense. And maybe actually a suitable refine should work, because here we see that I suspect that if you write something like refined match count with exactly these three cases, but you have the point is that you have to put the right thing here, and probably something like NS if true apply to E and NS, but maybe with additional arguments will work. It will be still nicer. Okay, so you can try. Okay, what time is it? Almost 10. Okay. Okay, so you have a similar exercise here. So if you plan to do this exercise, which would be a good thing, maybe you already did that actually, be careful to follow the steps before. Okay, so we want to prove that we can exchange the else and the then branch if you have a B naught here, of course, and in that case you just remove the B naught. Okay, so another kind of optimization if you want. Okay, and okay, so the point is that you need this theorem B is equal to neg B of neg B of B. So maybe it's already in the library, but the proof can be made in one line. So sometimes it's simpler to prove the things rather than to waste time in finding what's the name of the theorem in the library. But okay, as you want. No problem if you use the library. And anyway, the point is that using this one but use it properly, you can prove this. Maybe it's interesting to see what happens. Let me see. Well, level 1. It should not be complicated. So intros B, S, B, and some equality here. Yes. Oh, okay. So of course you should a little bit compute what you have in E. In. Yeah. Okay. So here you have something which which looks interesting. You have this expression which is here, but not exactly. Here you have a neg B in front of it. Okay, and you have this. Okay, so what could you do here? So once again, you should has been said what was before, what was stated before, which is this one. So you can replace any Boolean, but the negation of its negation. Okay. So what you can do here, for instance, is to so yes. Okay. So you can. The idea is is that you want to see this expression in the goal, but you don't have it. You have something which is simpler, but you see that this one is equal to neg b of neg b, neg b of this one, and then you have this one. So the trick is to say that you not to change, you rewrite your previous theorem here, applied to the left-hand side here. So parentheses are needed. And so once again here, be aware that this lemma is a function which takes a Boolean. My Boolean is here. And when applied to this Boolean, I get a proof of this equality. Okay, so again, if you are unsure, you can check its type. You see it's a proof of this, sorry, that this is equal to that. Okay, so as it is a so which means that you can replace this Boolean by that Boolean. Okay, and this is exactly what you want. So you can rewrite it. Okay, and you get this. And now you can use your equality because you have the negation, which is exactly here. Okay, and then it's easy. So the point here is that here you were in a situation. Oh, sorry. Yeah, I'm good. So I go again to this point. Okay. Here you have a situation which looks a little bit strange because you would like to use this equality, but you cannot. You can use this equality only if you have all of this at this place. Okay. Actually, there is another possibility. Okay, so I showed you one possibility, which was to use cleverly this one by replacing this one. Okay, because actually I focused on this expression that I couldn't that I have under my eyes. Another possibility actually is to replace B here. Okay, so it is also something which is interesting. So let us see. Rewrite E, but in the opposite direction. Okay, rewrite E like this. You can do that, and then then you have exactly this expression. Here you don't need reflexivity. You just can say apply my previous lemma. Apply neg B. So if you are very accurate, you say this. It is neg B applied to this expression. It's finished. And if you are lazy, you can say just apply neg B, because the second one is too long to type. But you should be aware that neg B sees what once again you have a kind of what is called technically a unification between this formula and that one, and then Koch can say, okay, so the suitable B is exactly this thing. Okay, so you can do things as you want. Okay, so the point is anyway that you need whatever the direction, it's okay. Maybe you can finish the proof, but it's much more complicated. So the point is sometimes to have this kind of things. So once again, the point is, okay, you have something complicated which contains this. You need to, in some sense, remove this neg B. Okay. And this is a common situation. When you see this one, actually, what you need, okay, if you know, it is the inverse of this function. And actually, the inverse of neg B is just neg B. This is why we had that. In general, if you have something like blah, blah, blah of this, okay, you should to find a suitable inverse of, left inverse of blah, blah, blah. Okay? So, okay. So mathematically, we say that neg B is injective. Yes, no, yeah, okay. Actually, I want to show you something else. Okay, it should not be there, but somewhat similar. Lemma, okay, not the right place. Not the right place. About numbers. For all n, if S of n is equal to S of n, no, this is so stupid, for n and m, then n is equal to m. It's a somewhat similar situation. Okay, so let us introduce, as usual, n, m, and e. Okay. Once again, I have something simple, which is simpler than the left or right hand side of the equation E. Okay. So the point is how to have something of Sn here. Okay. So do you have an idea? So the point is to say that, okay, replace n with, or actually we can even change it. Change, in that case, change n with, so up to u of S of n. What are the question marks? If I have the right, so I'm looking for a left inverse of successor. Do you have an idea? You have some experience with arithmetics? Yes. So we okay. So Fred is already defined. But we can okay. But you can just show it or redefine it if, as you want. So print. So I'm not sure that it is okay. This is what I expected. Something simple becomes something complicated. Okay. Okay. Init. .NET. .thread. Not maybe like this. Yes. Okay, you see that. So it's just a pattern matching on n, which says that if n is 0, I'll return, okay, we could say 0 or n. Okay, okay. For some reason, Coq defines the print in this way. And in the other case, so this is a fake case, actually. And the interesting case, here you could have, for this experiment, for other reasons, we really need n here to be, okay. But in this case, what is important is when n is a successor of something, we return this something, okay? So you see, okay, so here we can just check that the predecessor of S de n, of S of n, is n. Okay, so it's quite weird. Maybe it's better to write to define it by hand, but okay. Anyway, you have this. Okay. Then you can do a CBN. No, that's stupid. Don't do the CBN. Okay, so you see why doing so if you if you do the CBN, of course you have the wrong goal. Okay, this goal is better. So now I can rewrite E. Okay, and now I can do a CBN. Okay, that's finished. So this is this lemma here has a very general shape. Each time you have a constructor applied to a number of things. So if you could say something, I don't have binary trees here, but something like this, lemma. Okay, so I cannot, but okay. Okay, injectivity of bin trees. Well, I could use AAXP. Oh, yes. What is the definition of expressions? For instance, okay, I have B naught, I have B and. Well, let's just take B and, which is because B naught is like successor. B and, okay. Okay. So I will prove that B and is injective. So for all. So these are the Boolean expressions. Okay, so B and B prime. Okay. I need more. I need no, B1, B1, B2, B1 prime, B2 prime. Where is the prime here? If I have B and of B1, B2 is equal to B and of the same, okay. Shorter. This. Then, for instance, whatever, B2 is equal to B2 prime. I have the other, of course. Sorry. Okay. The semantics of conjunction is not injective, but here I am talking about ASTs. Okay, so these are it is at the moment uninterpreted concrete object. Okay, so don't go. Yeah, this is purely syntax, purely a tree. Okay, so I don't care what that it means. Okay, so it's an interesting reaction because you see you never okay. So let us introduce. Okay, I will put a star because I'm lazy. So it means the names which are before. So okay, so the names are controlled and some equality. Okay. So here, okay, so you have not a predecessor in your pocket here. So what you could do is the following: you could invent. So pose. Okay, F. Maybe we can even be shorter, but okay, I'll do it this way. So F of B match B with. So I will be as short as possible. So I will consider only the interesting case, B and of okay, B. Okay, I will use as a name in order to. Okay. In that case, I return C2. And in all other cases, I return whatever, B. I don't care. Something. Okay. So I hope that, for instance, B2 can be changed with F of this one. Okay. So as soon as my F is correctly defined, so the change works, and then I can rewrite E. So you see, it's easy. Huh? And then CBN. Okay, so you see the trick. You can play with it. Or once again, you can use a Coq tactic which does exactly this, actually. So you can, okay, so undo what? Undo 2 maybe? Or even 3. Okay, so 4. Ah, yes, because I have many leaders. Okay, let us. Well, Sabian is not useful. Okay, so undo 2, I think, should be enough. Yes, and okay, so there's a tactic called injection E. Okay, so Coq actually produce something which says, okay, if blah, 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 then okay, so you see that it is easy to prove now. What is interesting is to see how it works. You can print the proof to understand what happens. Print, no, check, no, show. Sorry. Okay, and you see that okay, if equal. There's something complicated here. But anyway, you see that you have this function here. The point is that you see exactly the function that we defined. Okay, actually you see one function. No, okay, no, sorry. This is the other function, and this is the second function. Okay, because you see here, you could focus on C2 because we need here, or you could focus on C1. So what Coq does automatically, because Coq tries to have all possible injections. Okay, he want to conclude the same thing, not only on B2 but also on B1. So it provides all these functions by automatically. And okay, produce this. So injection allows you to have all possible projections of your original tree here. Okay. So actually, okay, so this one is exactly this one, and Coq actually works a little bit too much, but it's convenient to use. Okay. But okay, basically it is exactly the same trick. Pattern matching. Okay. Okay, so it was E1, E2, and exact E2, E1. Ah, okay. Let us call them like this: E2, E1, and exact E2. Well, yes, by the way, you see that Coq produce an order which is not necessarily the one you would expect, but okay, for some reason it is this one. So this is a situation you could recognize, but beware. For the theorem we had in mind here, so the technique is more general. It works for when you have constructors like B and like S, okay? But in this case here, So this the case of the exercise here. The important thing is that you have a theorem not on a constructor. Of course, you have a constructor here. Okay, but let us forget it. Okay, you get this. So the point is that now the thing you have here or there is not a constructor, it is a function. So basically, what you need to is to use injectivity of this function. So what I just explained before is that due to pattern matching, all constructors seen as functions are injective functions, but you have also many other functions like neg_b. So this is a semantic function, by the way, which happen to be also injective, and b would not be injective. Okay, so we agree. This and the and b, I mean at the level of the semantics. Okay. Okay, so recognize injective situation. Maybe, well, maybe you can make a break here.
Yeah.
Okay. Ah, it's finished. Okay, this one is level 1. If you think, okay, if you proceed in this way, if you proceed in the first way I tried, it is you have to recognize a little bit more things. But okay, anyway, the technique is not difficult, but you have to know it. Alors, c'est bien quand on est arrivé, le truc était, ah, tu vois, comme ça, ça c'est super. Ah, ok. Mais c'est pas grave, je sais pas, il était là le plus noir. Et donc, heureusement, non, c'est pas grave. Ah, mais quand même, bon, alors, ça devrait dommage, je pense. Ça veut dire que c'est pareil, d'accord. En fait, ça veut dire que Donc, finalement, c'est une illusion. Il me montrait mon nom, je me suis dit, bah, c'est bon, il a reconnu, ça suffit pas. En fait, il a reconnu que j'essayais de rentrer par effraction. La police est en train de... Ok, je vais bien. No questions in the room? I mean, among you or... So it's good to have a rest because we start an advanced topic now. So we start now? Okay. Just a word before starting the second part of the lecture. So you could see that in Coq you have many possibilities. So you define your function, etc. And in front of goals which look okay, sometimes a little bit difficult or unusual or whatever, then you could scratch your head and wonder what happens, what you could do. And usually doing means okay, looking at the manual and saying what should I type in this situation? And looks like this tactic, blah blah or whatever looks fine. Okay, and then you try the tactic. Sometimes it works, doesn't work. Sometimes it works. So what I try to do here in my lectures is to always explain what happens in very basic terms. Okay, so even if in practice it's good to use predefined tactics because okay, they are convenient and so on, etc. But it is important to recognize the precise situation where the tactic say discriminate or inverse or injection applies. And it is so, and also by explaining that how it works, and it is sometimes it can be explained in very simple with very simple notions. Okay, and I think it's better because you understand that Coq there is no black magic inside. Everything at the end is defined by very basic programs, and it is interesting to understand what is under the carpet, and sometimes you can design your own way of using all these basic constructs, because actually Coq is made of very few basic concepts that you can that you are like me, you are programmer, so you can program with them, and sometimes, especially with a refined tactic, it is very powerful, and so you can have something which is actually much shorter than what you could reach with tactics. Okay, so we will. Okay, so I will first motivate the next thing by continuing by okay by okay by going to the next exercise. So okay, so this one is not. Okay, so at the moment, so I have a better a better script for inversion. So I will explain another tactic, very important, which is called the inversion. So let us define this. Okay, this inductive. Okay, so what is this inductive actually? A kind of subset or subcase of NS. Okay, so let me see you. Let me show you. Especially you have this one. Okay. Okay, so for some reason I will explain later, I define this one, which is a kind of copy-paste of this case and only of this case. I don't care about the others. Okay, so I say that okay, it is presented a little bit differently. Here, I1, I2, IS, and S2 are just parameters. Okay, I could put them here, but it is for some reason it's better to have them as parameters. Anyway, the important thing is that you see that in order to prove NS1 sec of I1, I2, SS2, like okay, which is similar to this one, except that the sec here has been removed. Okay, so I'm interested in this goal here, and I say that if I have like here exactly this, okay, then I have this. Okay, so I define. Okay, so we will see later why we write this one exactly. But anyway, I want to prove this for some reason. I want to consider it. So basically, it's a kind of subcase of NS written, okay, a little bit differently, but it's not important. So would like to have my windows. Okay. And the point is that I would like to prove the following lemma now, because you could see that this one was very similar to that one. I should not remove it, but the conclusion of NS in the case of sec was exactly this one. Okay, so I want to prove the following thing, which is that if I have NS of sec I1, I2, S and S2, then I have this relation. So let us see what it means intuitively. So at the moment, the goal looks a little bit artificial, but later we will see that it appears naturally or something similar appears naturally. So the basic thing is the following, okay? The point is that I have a goal made of hypothesis and a conclusion, and don't focus on the conclusion at the moment. The important is to focus on the hypothesis here. This is the important part of what I want to show now, is that I have a hypothesis like this one, which says that I have NS of some instruction in this form, and okay, S and two states. So remember. So okay. So okay. I prefer to have the original. Here. The important thing is that if you have this hypothesis, it means that you have a proof of this conclusion. And how this proof could be constructed? It could not be constructed, for instance, using this. Using NS if true. Why? Because the conclusion of NS if true is if blah blah blah. But I don't have a if blah blah blah, I have a sec. So in some sense, this one is not relevant. The same for this one, and the same for the following. The remaining one says that I have a while and a while. So all the last one are not relevant. The second one is not relevant as well because the first argument of NS here is an assign, which is not a sec. I consider that a sec is not an assign. A sec is not an assign. It is not, and here it is not a skip as well. Okay. So the important point. So it is similar to what we have seen before when you were discussing about discriminating. So I would say I would, in some sense, discriminate and say that the only relevant case for NS, which is this relation, is actually only this one. And so where? Okay, I am here. Okay. If you try. Until now, the only thing that you know is that when you have a hypothesis with a type which is an inductive type like NS, the only thing you know is destruct the hypothesis. Destruct it, and then you will get the 5, 1, 2, 3, 4, 5, 6, 7 case for NS. Okay. So destruct NS. And actually, so okay, as something I am lazy, just to show you that you don't get the right goals. Actually, if you write the simple destruct, for the moment, you don't get the right thing. You get many subcases. Actually, only this one is relevant. Okay? By the way, you can cheat a little bit. So let us forget the two first at the moment and consider the third one. And the third one, it's not even that sympathetic because I would like to have I1 here and I2 there. Okay, so so even for the third case, I don't have exactly what I expect. So you have to think a little bit to understand what happens, but the point is that destruct makes something which is, how to say that? I go back here. Actually, the destruct tactic forgets the precise shape here. If you write things like this, you could do a refine with something which is quite clever, which will work, but it is too complicated. So usually in this situation, you would like to use destruct, and destruct will not work. So the trick to know is that destruct does not work, and you use a magic tactic of which is called inversion. So inversion is like destruct, but it is able, in some sense, to see that this particular argument is special, and only then you get only one case. So it's quite difficult to read at the moment, but you can see that you have the right hypothesis actually. Okay, so NS has been decomposed, right? And also Koch adds a number of equalities which are quite cumbersome. So we can also clean them actually, or just remove them. Okay, so now we have something which is cleaner. But okay, but now you see that, for instance, in that case, you can prove your goal, because so remember that precisely the NS1 sec can be proved when I have exactly the hypothesis I have. So if I am able to decompose the previous goal in the right way, okay, so it's finished. Okay. So that's what inversion is able to do. Another, okay, so inversion is quite nice, but so it introduces names that you have no control on the names, and you have a number of parasite equalities. So you always have to clean a little bit. So okay, so in practice, it's convenient to use, but you have to be careful with these names. So I wish to show you that you can program your own inversion. So it's a little bit technical, but it uses only elementary things that you already know. So that's the very point. So okay, so I change. Maybe I should try this one. Okay. Okay. So I have a file here. I'm sorry, I did not finish the translation, but I will give the explanations. So later I will finish the translation in English of the comments. So I will, as usual, explain the technique on a very, very basic example. So always on colors. Okay. So we have our enumerated type of with 7 colors here, and we have a next color, I would say function, but it is a partial function. Actually, it is a deterministic relation which says that the next of green is orange and so on. Okay, so okay. So discrimination, I think you already remember that we have contagious equalities. So for explaining the discriminate, so okay, so this is something we have already seen. It's just remembering. So I say that if, for instance, I state that green is equal to orange, that in any type X, then any element of type X, they are equal. Okay, so so I just, oh sorry. Okay, so as usual, I invent the right function which says that green is mapped to X and all other are mapped to Y, for instance, and then X is just f of green. I can rewrite my equation here. Green is equal to orange. Okay. Okay, and then f of orange is Y. And then I am happy. Okay. Now, so this one, the nice thing with this one is that it just used the rewrite No, not the rewrite. I mean, the function, the auxiliary function here is just a very basic function which, okay, use pattern matching and returns another data, a basic data, okay? X and Y are in a type which is itself a set, okay? So it could be a natural number or maybe functions from that tuple, this thing, but okay, it's still at the level of sets or the very basic, okay, so the usual level. But actually, the technique can be used on larger types. That is, here I am able to prove an equality. Maybe we would like to prove something which is not an equality. So we could imagine situation where I want to prove something like, for instance, even over 5. Even a 5 is not an equality. But I can use still the same trick. If in order to prove even a 5, then I just say, okay, then as all numbers are equal, I can replace 5 by 2, maybe, or 0, whatever, so something which works, and then use this one. So I am still able to prove many other properties, provided, like even, provided these properties are provable for at least one inhabitant, for instance, for 0 or for 10, okay? Now, if I have a property which maybe could be proved, but I don't know, it's more complicated. It may happen. I could have something else than even something which involves prime numbers and say that whatever some theorem for coming from Fermat or okay, something very complicated. You don't know. We don't have a proof of the result. Then it's more complicated because, okay, still you have green is equal to orange, and you would like to say that, okay, my property, my P of X still holds whatever is P. Maybe P has some, okay, there is some somebody which is such as some X such as P of X, but maybe not. But in that case, green is equal to orange should be able to work as well. So, and in the following way, so I want to prove, so forget the French. Okay, I want to prove the following one. It means strong or large. Which says that if I have, okay, I took this time red is equal to orange, I changed my mind. I would like to prove that for any property P, then I have P. Okay. So here I don't have an element such as 5 or whatever to, okay, I don't have anything. I just have a property, an abstract proposition. Okay, so sorry. I'm here again. So let us introduce again our equality and P. And what could we do here? We can do the same. But here, instead of returning a basic value, such as the Y before or 5 when I was talking about even, I return P itself. So something which is larger, is something which is at the level of types, okay? I return P, and for the other, I return, okay, another proposition which happens to be provable. I return red is equal to orange, okay? It is also a proposition. So you see that in all cases, the result of f of c is a proposition, which can be P or this one. Okay. So at the moment, nothing. Okay, I just put in definition which is well typed. Okay, it takes a color and it returns a prop. Then I say that P is just F applied to red. Okay, so you same trick as before. Now I can use my equality. again, some simplification, CBV or CBN. Okay, CBV works as well. And got, of course, this right-hand side, which can be proved here. Okay, it's just E. I should. Wait. So similar, another similar thing. So same goal. This time, instead of using this one that I had, I could another one such as 0 is equal to 0, for instance. Okay, so whatever. I just need to have something which is easy to prove. Okay, so f of red, sorry, p. I don't know how to prove it, but I change it, I rewrite, and now I have something which is easy to prove for another reason. 0 is equal to 0. Okay. Okay. So, okay. So now the good news is that you have this tactic I already told you about, and this which is called discriminate. You just say discriminate E, and it's finished. And okay, if you look in the details, it's quite the proof is probably. So let us show proof. It will be similar but a little bit different. Okay, so this one corresponds to the rewrite. The point is that here you have the function that which is similar to the one I defined, but Koch used other predefined propositions which are called true and false. And okay, at the moment I don't need to tell you what they mean, but you could actually you can. Why not? Why not? But okay, actually, definitions are not really needed. As you could see, I could just use P or anything which is easy to prove. So okay, well, let us print false and true. I will start with true. And true is just an inductive property which happens to be provable by this constructor. Okay, this is some property which is okay, just provable like using I. Okay, so it may look a little bit artificial, not always. Okay, so it does not carry any information actually. Okay, it's like a type, kind of unit type. Okay, a type with only one constructor, which is called I. And now let us. But anyway, it's different from the Boolean. The false is similar, but it's still it's even simpler. It's an inductive with 0 constructors. Okay, actually we could define an enumerated type, inductive, empty, like this. Okay, I have 7 colors or 3 colors or no color. And let us see what I can do with that. Of course, if you want to make a value in empty, it will be difficult. Okay, definition. Empty. If it is a color, okay, you can say, okay, color. You have many empty. Here you are stuck. How could you? Okay, where are the constructor of empty? You have no way to construct it. So basically no way, unless you are in an inconsistent environment. Okay, but okay, we will see that later. But on the emp2 color, so okay, let's do it. I can make it interactively, for instance. So let's say it is a function from an empty type to I need to provide a color. So first possibility, of course, is to provide a color. Exact, don't know, red, for instance. Okay, it works. But I have another possibility, which is to say, oh, I have here an interesting value within an interesting inductive type. So I can perform a pattern matching here. Okay. So let us say destruct to see what are the cases. How many goals after that? Basically, when I have a destruct of an inductive type, I have as many sub-goals as the number of constructors of the type. So 0. Finished. Okay. Of course, you can show the proof, or you could, of course, also write it directly. The function, it takes E of type empty, and it says match E. Okay, I return a color, but the point is with, and between the with and the end, there is nothing. Okay. The right thing to do is here is directly to say, okay, fun E match E with finished. Okay, so you see that when you have an empty type, it's very interesting. You cannot make an inhabitant of it, except if you have already one. For instance, of course, you can so no. For this, you can reuse the same code, of course. You can reuse this one, but you can do something else. So it works, but you can do simpler. You just return E. Just to say that beware, you can make an empty. You can construct something in an empty type, provided you have an environment which contains something which is empty. Okay, so it's what we call sometimes an inconsistent environment, but okay, but from the computational point of view, it makes sense. I just take, so you could have some things more complicated. You could have, for instance, you could have a function f, sorry, I don't get its name, a function from not to empty. And okay, so in that case, you would say fun f E, and you return, for instance, F of 3. F, no E, sorry, and F. Okay. Here you have many empty values, infinite numbers. Okay. So just to say that, okay, an empty type looks impossible to prove or to make, and okay, again, false. For false, it's the same. False is exactly like empty, except that instead of a set, we have a prop, but it works exactly the same. Okay, so you can make a color from false. Okay, you can also prove any property if you have false. X false, X falso, something like this. You can say lemma X falso. Say that for all P, which is a prop, well, okay, but false implies P. False implies anything. So again, so this is a law, a very basic law of logic, but you see that once again, there is nothing magic. It is just programming. So let us program a little bit. Proof. Okay, so I say impose P and some proof of false. Okay, and I just say destruct F. Finished. Same thing. Okay. Okay, so the empty type can be useful, and use it for its own discriminate tactic, but we can also proceed without these additional types. Okay, it's a matter of taste. The important point for this strong discriminate is the fact that here you always have a function which takes a value and returns a type or proposition. So you remember it is exactly the kind of thing we used before with the WOW program. Remember the WOW program? It was a program which takes a color, a traffic light color, and returned a set, like color, nat, or something like this. Yes, we have seen this in this one. Okay, maybe I will open it separately, just to remember that we. Yeah, this one. So I took a color, so a data, an ordinary data, but I don't return an ordinary data or a function or whatever. I return a type, okay? And here I decided to return nat or this one, and then I was able to use it. So the ability to define this kind of function or to perform this kind of pattern matching here, which is I take a color and return a type. Okay, so here the type is set, and in my previous example it was a prop. It is what it's called in type theory a large elimination. Okay, so this is something which is quite powerful. Okay, so just to show you that we already have seen this power of COP, and this power is used here. Okay, so different way. It is we have shown this way, with this one, with this one, and Coq used true and false, but okay, it's basically the same, true and false at the same level as equalities and so on. Okay, so that's just to say that discriminate, so we is something even stronger. And now let us consider Okay, so I have to move, okay, to this point. So, okay, let's introduce what we have. So I have two colors, C1 and C2. I have the fact that C1 is equal to orange. I would like to prove that the next color of no, sorry. I also have that this relation. Okay, so intuitively, but yes, then if C1 is orange, then C2 should be red. Okay, and it is exactly what the goal that we have here. Okay. So one of the things we can show here is that we can reason by cases on C1 and we'll see what happens. And the point here is that if we reason by case on C1, it's interesting to see exactly what happens. And so, because if we reason by case on C1, it will have an impact, not especially on the goal, sorry, on the conclusion of the goal, because the conclusion of the goal does not say anything about C1. Actually, what is interesting is to say, okay, I want actually use the information about C1 in the hypothesis. So in order to see things more clearly, it's better to have this one back to the conclusion part of the goal. Okay, so I already told you how to do that. You can do that with a refine. Okay, so it's like this. And so this is okay. I say that I have a function applied to this. Okay, I don't want to talk more. There is a technique in Coq which performs exactly this refine, which is called revert, and which is easy to understand. So we just this is the converse of intro. Okay, so I have this, and now if I reason by cases on C1, it is clear that okay, it will have an impact on the goal. Okay, this is easier to see. So what I say here is that actually this equality is like a Trojan horse. Okay, so the English name is. I start my translation. Okay, maybe you know this name. You know the famous legend. Okay. So the idea is that okay, you insert a horse here, which contains some warriors that will be able to fight and conclude the exercise. Okay, and now okay, so now we perform a refine pattern matching on CS. So here it is written using the refine, and we say that, okay, let us read what is written here. Okay, so we have CS. CS could be either CSV, CSO, or CSR. Do you remember these three constructors? So maybe we can put them. Okay, it is exactly the definition of next color. Remember, we have a next color here. Okay, I have a next color here, which is defined here. So you know that CS has to be either a CSV, a CSO, or a CSR. Three cases, and in the first case, for instance, CSV is a proof of next color green orange. Okay, which means that will be green here, and C2 will be orange. So here, what you will get is a goal where C1 is green, so we'll get green is equal to orange here. Okay, and on the right and of the arrow, C2 will be orange, so we will get orange is equal to red. Okay, so you see that it is exactly what I expect. For the other, I am a bit tired, so I just put a wild card. Okay. Okay, and I get exactly what I said, and Coq is able to provide, to fill properly the goal by replacing respectively C1 and C2 by the corresponding colors as defined here, as defined in next color. Okay, so I will get 3 goals, and then I think we'll be able to manage this. So let us show something else. So because we see that in each case I get an implication, my Trojan horse. Okay, so I will do an intro and we'll do this intro in each case. So I want to say this match. Okay, see here I was very explicit. So this match will be explained with written with a destruct, 3 cases, and an intro. So let us go here. We restart from this stage. So pattern matching on CS, and then introduction of the Trojan horse. Okay, so we get 3 goals. And this is just to say that actually if it is just to explain you that destruct, you have to, it is good to be aware that the tactic destruct does all this work directly. I mean, if you go back to this stage, if you just say destruct, actually, what is performed by Coq is reverting this equality because, this one, because Coq sees that C1, which is here, this C1 is interesting, so it is better for this CS to be here. So Coq actually performs a revert of CS, the pattern matching, and then the corresponding intro. Okay. So the destruct actually is complicated. If we could show proof, you will see that what is exactly performed by Coq here. So you see match. Okay, he says, okay, yes, you see that you have the implication, and then in each case you have fun, etc. So the fun performs the intro. Okay, actually, as I named. Okay, we will see the name. Okay, maybe it will be E2 or E1. Okay, this is a little bit clumsy to read, but the basic point is to understand that actually it is equivalent to revert, then match, then fun, that is intro. Okay. So we have these 3 goals, and now let us look at our 3 goals. Here again, I recognize a green equal to orange, so I could play with contagious equalities, or I could be okay. I can use my previous theorem. Okay, in that case, I kept this theorem which says that if green is equal to orange, then any x and any y of the same type are equal. Okay, so I just apply this theorem by first argument the equality E1, and then so this type. Okay, you remember with these curly braces, the type is implicit. We don't have to write it explicitly, and because we follow by 2 elements of this type. so I apply my theorem applied to E1, then to orange, then to red. Okay, you can check that the type of this is that orange is equal to red. Oh, sorry. Okay, so this is exactly. So I could, okay, or could say even exact. Here, okay, well, I will keep what was written. I rewrite and reflexivity, but I could also say directly exact. Okay, next one. The next one. I have orange is equal to orange, which is contains 3. No information really here, but the goal is easy. Okay, red is equal to red, so okay, reflexivity. And for the last one, okay, we can reuse the previous one. Maybe, yes, because I worked a lot before. I used it was called strong. Or I can just use the one here, the tactic of Koch, discriminate, which does the same work. Okay, so let us do this very shortly. We introduce these 3 things. And we say, again, we can see the trick I said before. I will try discriminate in all cases. So I destruct CS into 3 cases. And I guess that in a number of cases, this equality here will be specialized to something which is such as, I don't remember, green is equal to orange, red is equal to orange, something like this. Okay. So equalities which are some absurd, so which can be dealt with using this tactic. So I will, okay, so I will try this tactic systematically. And then only one case is left, which is the case where I think it's the middle case, but whatever, which can be proved by reflexivity. Okay, so this is very short. Okay, so the take-home lesson is that, okay, in this situation, you can do something and follow by try discriminate when you know that you have many cases that can be automatically finished in this way. Okay, so let us now try a more difficult one, because you could think that we have enough, sorry, I have to go here, yes. So I want to prove that systems, okay, let us introduce 2 hypotheses. So I have a color, and I have the fact that the next color of orange is C2. So it is the converse of the previous theorem, actually. Okay, so I am just looking, because actually this part was written by my colleague, but I think sorry. Oh, okay. Let us try, but I don't think it will work. Right now, discriminate or after the destruct? No. Oh, okay. Let us try. We have nothing to discriminate. Oh. Yes, here we are very stuck. The point is that what happened here? Destruct CS. Okay, actually, Koch just said that. Discriminate here. No? No, discriminate works only if you have an equality. I don't have an equality. So it's possible that inversion works, because inversion actually works in many. Inversion means many things more or less similar, but which are not really exactly the same. So Okay, and so in that case, if you really want to explain what happens under the carpet, so it's let us see. Yes, you are right. You are right. Yes, it is a typical case where inversion will work. Yes, but precisely now I want to explain what is how it works. So okay, so you can use the tactic inversion. I agree. I agree. Let us try an inversion CS. And okay, so C2 has been replaced by red.
Yeah.
So it works. Okay, I agree. But now I want to try to explain how to do the same using only basic definitions. Okay, so basically after a destruct here, okay, so actually the important information has been lost. What I explained before on a more complicated case, but the point is that some rewriting has something has been done, but we lost the information in this hypothesis. So in this case, actually, it's possible, I think, to let me see. But I think that it's possible to reason by injection. I think it is what he did. So actually, okay. See here we define three functions. Okay, no, two functions which returns green for 0 and red for s of p. Why not? And another one which is orange for 0 and green for s of p. Okay, let us see what happens here. Okay, we can, and okay, it's quite indirect, and we can show the next lemma, which looks quite quite strange because nothing to do with what. Okay, but okay, why not? Let us see what happens here. We introduce our two numbers, okay, and the point is that okay. Actually, I don't care on the only care on the fact that this this expression here and the same is here. Okay, this expression is actually has only two possibilities: 0 or successor of something. Okay, so if you write this way. So here it is with a refine, which is very explicit. Okay. So you see, so what is to see here is that when you have this, you have more information. You have that we have a number which has a precise shape defined with n and m. But when I say, okay, I look the possible shapes for this one, I just get a 0 or s of p, but I lose the relationship with n and m. So let us see. Yes. So this is just the refine mode, but you can do the same with the destruct. Okay. So this is similar with the destruct we had before. Okay. So if we destruct this expression, I get exactly the same. I have two cases. So now what happens? I can compute. Ah, nice. I can show it. Okay. So what happens here is that not me, but my colleague, because I think it's called Pierre Coppeno here, has been very clever. He invented very strange functions here, which happens to be able to prove this strange lemma here. But it's not finished because I think okay, so just to show that we are able to prove this. Still, I'm not sure that we are able to prove that. This one. Actually, I think we are a little bit far away. Let us see. Oh, maybe we can. Okay. What happens? So, okay, so same statement as before. So always the same. So we see that. Okay, so here, okay, we are stuck here. Because we lose the information, but I think that now he will probably change this. Okay. Okay, so we abort actually. Okay, so the point is that here we want to remember that the information which was contained on this equality here. Okay, here. Okay, we want to keep this information in a better way. So here is a possible idea which works quite often. We call it a souvenir. So it's a French word, but I think it also exists in English. Remember, okay, about orange. Okay. So I want to prove this one. I want to prove that, okay, let us introduce to see that more clearly. If I have some property of color, so a predicate on color called P, and if I have this thing here, which says that if for all C a color, if C is equal to orange, then P of C. So it is not, okay, this is a predicate which satisfies this implication. Okay. Then I can prove P of orange. Well, it looks quite easy. So yes, it's very easy. So, okay, so basically this lemma is very, very easy. What is important is that we can use it later. This is the important point. So of course, I just apply this one because I recognize P of C by putting C is orange. Okay, and I got, okay, reflexivity because, okay, now we see the orange. Okay, so no surprise here. It's very, very easy. Okay, and we can even prove a more general version of this lemma, which says that if I have a set X, some Y, such that P and P of a predicate on X, such that for all X such that X is equal to Y, then I have P of Y. Actually, it is the Leibniz principle. Yeah. Okay. It was introduced to see more clearly, but you see it is just like before, but okay, with more parameters. So I have a general X instead of color, and we have a general equality. Okay, but so that's the same. I just apply my property here, and I am left with an equality, which is provable by reflexivity. So the point is that now il y a ici juste KZQ. Complicated. Ah, okay. Usually we use the other way. Usually we, okay. Okay. So here, just to explain this tactic, which is called KZQ, which, and then to explain KZQ using the previous lemmas. So KZQ is like an improved destruct, which remembers that that this expression here, so which will be either 0 or S of something, comes from this. So okay, we want to keep that the 0 or the S of something is this expression here, okay, is equal to it. So hence the name K is a Q. So let us see what you get here. This KZQ is sometimes quite convenient. So you see that here you get the two subgoals, a goal for 0 like before and a goal for S of something like before, but you also get an additional hypothesis here, okay, which could be used if needed, okay. So we can introduce E, and okay, so here there is no point to. The point is to see that here you get the fact that you have your exactly the same goal as before, but we remember, this is a souvenir. Remember that okay, that the number we have here comes from this expression in the two cases. Okay, so let's go back from the very beginning. So here. So okay, to show another thing which is called pattern. It's a little bit far from what I wanted to show today. So I'm not sure that I will insist too much on these details because they aren't interesting, but okay, so maybe, okay. Okay, so I go to this here a little bit quickly. So here I show you not technical, which is interesting, which is called pattern, which is something interesting. So pattern has an argument here, which is an expression which occurs in the conclusion here. Okay, you see two occurrences of this thing. So when you say pattern, it is like a change, but it is actually a special kind of change. You could write this by yourself, and you see that it is a function of. So you recognize exactly what you have before. Function of something applied to this thing. Okay, so you have P, some property P applied to this expression. So let us undo it. Okay, remember you have this one. I would like to say that it is some property of this one. So you have to isolate this one here. So it is called N0 in the next line. Okay, and you get it. And the point is that now you have some P applied to something, and this, so here you can apply our lemma called souvenir. Here, okay. So I have a special P here, okay. So we can apply it. So let us see what happens. So I have this one, apply souvenir, and it says that, oh, for all x, such as x is equal to blah, 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 then here. So so this one is quite nice now because we can introduce this. And now we can perform equality, okay, in 3m is equal to this. So we introduce a number which is equal to that. And the point is that now, instead of having a complicated expression, I have just a variable. This is a very important point. I have a variable which is equal to something. So now, okay, the basic destruct can do what he wants. He can try to forget what he does. I don't care because actually, no, actually, destruct will takes into account that N3M is there, so it performs the revert, pattern matching, and intro. Okay, it performs all this, but you see that here you get the equality. So the point is that using souvenir and destruct, the full destruct, you have the same effect as this KZQ. So it's quite convenient because you don't have to write all this definition, but you see KZQ can be once again defined in very simple with very basic constructs. So here, okay, we can finish as usual. The point, okay, the point is that it's not that we can finish the conclusion. The point is that in our pocket, we have that S of P or 0 comes from an original expression. Okay, so for this theorem it's not important, but for the original one it is important. So let us see this here. So this is the one we wanted to do. Okay, so intro. So if you try the destruct here, you get nothing special. Once again, if you destruct, okay, no, okay, I should intro some next, followed by destruct any. I can. Okay, you remember we get, in this case we get something which is unusable. So I forgot this one. Now as in the previous exercise, I perform a pattern on orange. Okay, so I get a property of orange. I apply my souvenir lemma. Then I introduce a number of things, and I get something which is more interesting. I get that I have C2 is equal to red, but the important point is that I have this additional equality here. Now, if I destruct CS, then, okay, let us do it without cheating, without, okay, slowly, I mean, that's what it's slowly. Okay, you get your three equalities, but to be proved, but you also have an interesting hypothesis which can be used. But in the first case, you see, I have green is equal to orange, and you know that in that case, we can prove the whatever just by using discriminate. Okay, and I will have the same in another goal. So this is why actually I try discriminate in advance. Okay, and I get what is equal to red. So okay, so here I was able to do that. Okay. Okay. So okay, some comments here, so I will translate them. Now that's for Yusin. Yeah, you have the powerful inversion. Okay, which okay, finish everything. Okay. So, but now if we
apply pattern and then followed by pseudonym.
yes, you could do KZQ as well.
Yeah. So the pattern, you abstract.
Yes. So yes, so maybe it's good to see that the point is a souvenir. No, voilà, the general souvenir. Okay, this one.
4x is equal y period.
Yes. So you have a goal which has a predicate of something, so you have to isolate this predicate, and maybe this way as well. Once so this is the creative part, okay, in some sense, and then you say that in order to prove this, it's enough to prove that for all x equal to y, then p of x, and this one is trivial. But the proof of this lemma is trivial, but the okay. So you see that once when you apply this lemma, then your conclusion will be this one. Your next conclusion will be this one. Okay, maybe we can try to put this at the top, or maybe like this. Okay, so this is a statement of souvenir. So the proof is easy, it's not important. Oh. Sorry. like this. I want to go to the other window. This one. Okay. Okay, so here I put orange in the conclusion in order to be able to have a pattern working. Okay, so I isolate my orange because it is the thing I want to reason about. Okay, so this is some property of orange. Okay, and by applying souvenir, I get something similar, but which is not for. Okay, how to show? Okay, I have this applied to orange. Now I have, okay, after the apply, actually the P is reduced. Okay. Maybe if I do this, it's easier to see. Yes, I think it's maybe, okay, because you have less thing to read. So you see some property of orange here, okay? After applying souvenir, okay, so this orange will become an abstract X, which is equal to orange. We will say for all X which is equal to orange, then this implication holds. Okay, so let us do that. Okay, you see, for all X which is equal to orange, then, so this is, before you had orange here. Okay. So nothing surprising. Yeah. It is just a restatement of the previous one. It is really equivalent. Okay, and easy to prove. But the point is, you need to put it in this form. You have to put the goal in this form in order to have a destruct which works properly.
Otherwise, you destruct
Yes, then you can destruct. Yeah, you need to destruct CS. So CS.
Next column.
Yes.
Then you destruct
Yes.
Now you remember C1.
Yes, actually, yes. There is another thing to see here. Here CS has a type next color of C1 and C2, which are two variables. Before I have next color of orange. You see, it was a specialized. So it is the reason why I was unable to have an interesting pattern matching, because the basic pattern matching on a next color is to say, okay, I have three possibilities for next color, and okay, so it's better to have, as soon as I have a variable here, okay, it's okay, so the pattern matching will not lose anything because, okay, anyway, the important information is here. I keep in mind in my pocket that C1 is not anything, so you could. Okay, basically you should say, now I revert this E1. Yeah. And then I perform pattern matching on CS. And then okay, so this is a Trojan horse. Yeah. Okay, you introduce a Trojan horse.
Then I'll go back to the souvenir. Can we
this one?
Yeah. Here you define that one. I modified, for example, you have a parenthesis before P1, right? I remove. I remove it.
You can try. So you suggest that now I remove this.
Let me see if this is correct. For x equal 1, x 需要这个 correct 了。
Okay, so what I have in P, and then I have something which is I have a X, I have an equality, and have a proof of Px.
So this is right.
Yes.
So this is correct.
This is correct, but it is.
I use this for the next proof.
So, okay, just finish the proof. So, okay, I will write. Okay, I will say it's shorter. Case E, but okay, and exact X. It's weaker actually. But okay.
Yeah, no, it's weaker. And one.
Yeah. Oh, okay. Okay. Interesting question. Okay, so I have this one. Now, Alt.
Yeah, this one. No.
He went. Okay. Let us see. Yes. Apply this one, but I need to provide a witness for X. Which X do you want to choose? The only the only possible one is orange. I guess, I think. Or can try a E-apply.
No,
Simplify when?
This can be computed.
Here, there is nothing to compute.
Yeah.
Okay, I can. Okay, I can back here. Okay, this is the original goal.
This is the original.
Okay, so.
The X.
Yes, so we want to prove something on orange after the pattern, and then if I want to use this one, I need to provide some X which is equal to orange. So on orange, if I try something else with red, for instance. No, it's not a good idea. Okay, you agree? It's better. Okay, let us try with orange. Now, okay, this one is reasonable. Okay. And then I think we are back to the original. Okay.
It doesn't work.
We are just looping. Okay, so the lemma is correct, just useless.
Yeah.
And you can see it actually because you can see it because this P of X is exactly what you need to prove from the very beginning. So yes, so the parenthesis here makes sense.
Yeah.
Actually, maybe a way of reading this one is to put parentheses and replacing the for by an exist. I think it's the same.
Exist?
Yes. If you write this, but okay, I don't want to talk about exist because okay, this some exist maybe like this. I think that the proof is the same, but you have to understand what is. But okay, if you write this way, you get the same. Maybe. maybe something like this, maybe. And I have another one. Yes, it is still okay. No, it is yet another one. It is an intermediate between yours, but anyway, it will be useless as well. I think. Yes, okay. Bon, okay. No, so don't talk about exists. Okay, what time is it? Okay, maybe time to finish, maybe. Yes, okay. So if I'm not wrong, I think we can go here. Okay. So, okay, I broke my my script. Oh no, no, not that difficult. Like this, I think. Yes. Okay, but I think okay. Well, let us finish. So intros X equality and next color. Ah no, okay, it was here. Okay. Okay, so we are back to this one. So we know a little bit about, okay. Okay, let us try a color which has no next color, purple. You remember only green, red, and orange have a next color. So that's an interesting case. Okay, so let's write it in English. Nothing follows purple. So what I claim is that for this one, I can prove the next theorem, which says that, okay, so I have a color. I claim that this color follows purple according to next color. We have no such color. So intuitively, this hypothesis behaves exactly like the empty type I presented to you before. Okay, it was not my intention to anticipate this one, but we can read it in this way. And actually, inversion, we will recognize this by magics. Okay, so let us try to understand what happens. So once again, we put this hypothesis in the conclusion, and we will try to apply our previous trick. So here the important color is purple. So let us see it and apply my souvenir lemma. Okay. And again here, I can perform a pattern matching on CS, and CS will always identify C2 or something, but C1 will be enforced to be either green, orange, or red. You remember, index color is only defined when C1 is green, orange, and red. So C1 here, the effect of this, C1 will be either red, green, or orange, and then we get an equality, which is once again a contagious equality, so which can be dealt with using discriminate. So okay, so I prove. Oh yes, I prove any property P in that case. So I have green is equal to purple. Okay, discriminate, etc., etc. So you see, okay. So that we can prove. What is the next one? Yes, it is to illustrate the subsyntactic, which can be used sometimes. So I want to prove the relational equivalent of one of the first theorems, maybe the first we had, which was that the next color is the original color. Okay, here it is written in so it's less convenient with relation. You have to name many colors and say that the next of C1 is C2, etc., etc. And at the end, what you get is C4, which should be equal to C1. Okay, so here we have many hypotheses. Okay, 4 of them are here and the 3 here. Okay, so let us start smoothly. So here, okay, it's reasonable to start with the destruct of the first one. Okay, 3 cases. And what we see is that, once again, we get an X color of orange something. Okay, so again, we see an opportunity of using inversion because here it is not an X color applied to a constructor. Okay, so destructor, you recognize this situation. So inversion is better than the usual destruct, the simple destruct. Okay, so again, you see that inversions always introduce cumbersome equalities. So use subst just to clean this. Okay, and then the next one we get a red, so we can invert it again. Okay, and at the end we get green is equal to green. So here, what you can do this, and you have to do this 3 times. So again, here you can do this with one command, so introductions, and then you say, I reason by cases on C1, then I will invert CS2 and then invert CS3. So maybe with a substance in the middle in order to have something cleaner, and finish by reflexivity. Okay, so all the sub-goals, because if you don't do that, you will have 3 goals and then inversion will provide you only once. Okay, but still it's convenient to reuse the same line for all these cases. And okay, so here is an interesting use of inversion in a sequence of tactics. Okay, and here is the real things that I would like to show you. So, okay, this will be the topic of the next lecture because it's time to finish. So we'll see how we can do our own inversion. So the previous things we did were some kind of interesting but indirect uses of destruct and this souvenir lemma, but it does not work all the time anyway. So inversion is more powerful than that. And we will, next time we will explain an interesting implementation, say, and of inversion that we call small inversion, and it will be used in particular for proving interesting things on semantics, on natural semantics. Okay. So thank you.
No, I still have a question.
Yes.
I'm still wondering how the souvenir is defined. I have another version of souvenir. I don't know if it works or not. Can you go back to the souvenir definition of souvenir.
It is.
Yeah. Now let's make another version. Okay?
Oh, sorry. Yes.
Yeah. Can you copy this? Yeah. Okay. Make a new one.
Okay.
I think the order x equal y plus px is not important, so I can't just work the px with x equal y. So for all x, you say for x.
Here?
Yeah. Instead of x equal y plus px,
yes,
you do the inverse. The px implies x equal y.
Okay.
And just one is this one.
Like this?
Yeah. No, you cannot prove it.
This one cannot be proved.
Oh, cannot be proved. No. Okay, cannot prove this.
Yes, you have nothing. Yeah, you have no conclusion of P something. Another version?
No. Okay.
Or in the classroom, maybe some of you have other suggestions. Okay, so still, this one is interesting because you see the statement is very short.
Yeah.
Very okay. Okay, you maybe need to think a little bit to understand because it's deeper than you may expect. Because you see that you know. Okay, I mean this one. Sorry.
Yeah, I think there should be other definitions. Still works, but not in that shape.
Mainly because actually, so if you can recognize this is exactly the Leibniz principle actually. And so this is basically equality. Actually, you could even define equality in this way by removing this one. Okay, yeah. You can have this definition, which is, and in that case, I have to see, but I think it works. You can do that. So Leibniz. Sorry, we need this one. Yes. So x is equal to y. Okay.
Let's say, no, see, I'm not working, sorry. I'm very...
Okay, this is more complicated than one. Okay. So you have another one? Okay. So I should take this one as a model.
Yeah. For x equal y. Instead of writing px, you write py. I think it's the same.
Py here?
Yeah. It's the same. No?
I don't think so.
Why?
Sorry. So you need to provide an instance. You need to provide x. So yes, you say maybe y. This is the only one you have. So you can prove it.
And then can we use this version of souvenir for your next proof? this one.
This here? Oh no, no. Yes, this one.
Here. Still one is we don't have hard.
The problem, I think that the problem is the equality here is just disconnected because now you can reason by case on this one. By the way, okay, maybe this orange will be recognized here. Maybe. Okay, let us try.
This is right. Blindly, that's right.
Yes. No. No, because here you need to prove this one. So this one is impossible unless you have something which is false in some sense. Okay. But here you have a C1 that we don't know which is equal to green. But C1 could be green. The only thing you can do now is to by case on C1. And you have two cases which are good, but one case which doesn't work. This one is okay, and this one will. I think it's the same as this one.
Yeah.
Okay. Interesting. Okay, so thanks for the suggestion and for participation.
Okay, thanks for the lecture.
So see you next Friday. Okay.
This Friday.
Okay.
I can stop sharing.
Ah, yes. Stop share.
Okay.